Hey guys, sorry that I cannot be there today with you guys, but I'm going to go ahead and do my best to give you what the notes that you should have. So basically right now what we should notice is that instantaneous rate of change, we've already talked about, is the derivative of a function. Those two things are synonymous. We also think of this as the slope equation. Speed, however, is the absolute value of the derivative because speed is always positive. So when we look at this next question, example 2, the position of a particle is given by the equation of motion. We've got it here, 1 over 1 plus t, where t is measured in seconds and s is in meters. Find the velocity after t, or after 2 seconds. All right, so looking at this, our t is 2. So if we think of what the definition of the derivative is, we need to think of this as the limit as h goes to 0 of f of, in this case, we're not going to say x plus h. We know what x is. It's 2. So 2 plus h minus f of 2 all over h. All right, so taking a look at this, if we go ahead and plug it into our equation, we have 1 over 1 plus 2 plus h when we plug in f of h minus, and I already calculated what f of 2 is. It happens to be 1/3. That's all over h. All right, so really this is equal to the limit as h goes to 0 of 1 over 3 plus h minus 1 over 3, and that whole thing times 1 over h. If you remember last week, we talked about that when we divide by h, we're really multiplying by 1 over h. All right, so looking at this, if we get an LCD, we know that first fraction is missing the 3. The second fraction is missing the 3 plus h. And that's all over h times 3 plus h. All right, so if we distribute that negative symbol, the 3's will cancel. We'll be left with negative h in the numerator, h times 3 plus h in the denominator. And if we go ahead and reduce, we end up with the limit as h goes to 0 for negative 1 over 3 times 3 plus h. And again, I just reduced those h's. All right, now if we go ahead and apply the limit, which means that we plug in 0 for h, I get negative 1 over 3 times 3, which is 9. So I know that my velocity is negative 1/9 meters per second. But because speed is the absolute value, I know the speed is positive 1/9 meters per second. Remember, the velocity gives direction and speed, whereas speed is just how fast I'm going, not concerning the direction. All right, next we're going to go ahead and talk about what does it mean? What does the derivative actually mean? Remember that the derivative is an instantaneous rate of change. So I have 3 scenarios here where I'm asking you to find the meaning of f prime. So we have the cost of producing X ounces of gold from a new gold mine. I want you to keep in mind that at first when we produce gold, it's going to cost a little bit more money at first. We're going to hit that maximum amount of production that's going to yield the greatest amount of profit. And then slowly we're going to start to lose profit because eventually we're going to have to dig deeper and deeper and deeper into the mine in order to mine the gold. And so it's not going to be as cost effective to continue. We kind of have to determine that special number where it's time to be done producing gold. So in this first case, it says, what is the meaning of f prime and what are the units? Well, for this scenario, f prime, again, is an instantaneous rate of change. And in this case, it happens to be the rate of change at which the cost is changing per ounce of gold produced. Our units for this would simply be dollars per ounce. Remember, anytime we have an f prime, we're dealing with a rate. So it better be a ratio for our unit. All right, going to B, it says, what does the statement f prime 800 equals 17 mean? Well, that's a simple answer for that one. It's simply saying that after producing 800 ounces of gold, the cost per ounce is $17 per ounce. So we have to produce 800 ounces, and that's our cost per ounce at that point. All right, for the next part, it says, what will happen to F prime over the short term? Well, over the short term, F prime is going to decrease. Eventually, it may increase, though, because to extract the gold, it could become more increasingly difficult with time. And so in the long term, that's going to increase, but short term, it should decrease. All right, moving on to instantaneous rate of change. You guys have seen this, I know, in your science classes, and hopefully you've seen it in some of your math classes, that the delta or triangle means change. So change in y over change in x, and hopefully that reminds you of slope. And in looking at this formula right here, it reminds me of slope. I have a y minus y over x minus x. And what we were saying is that the two x values are getting close together, as close as I can possibly get. In fact, it's saying that I want the change in x to be 0. So it's very similar to our other equation that we have with the difference quotient. All right, continuing on with our notes, we have this example 4 here for us. And it's basically talking about a particle that's moving along a straight line. And it has an equation for its displacement. We are asked to find the average velocity over each time interval. And now average velocity, if you think about it, and what we've talked about in class, average velocity is referring to the secant line. It is referring to 2 points that we can actually find the slope between. All right, this interval that is marked right here is what we're going to find the slope between. So in other words, we are going to figure out what S of 4 is, what S of 3 is, subtract those two, and then take those x values of 4 minus 3. If you go ahead and plug that into your calculator, you might want to pause the video to do that. So in other words, plug in 4 to our S function, plug in 3 to our S function, subtract them, and then divide by 1, and you will find that you get an answer of -1 meters per second. Now I'm going to go ahead and apply that same thing for the interval 4, 5, which means I need to find the function's value at 5, the function's value at 4, subtract those, and then again I'm going to end up dividing by 1 because there's a difference of 1 in that time interval. When you do that, you're going to get an answer of 1 meter per second. All right, so if we think about this, we're supposed to find the instantaneous velocity when t equals 4. Well, if we know on the left side of 4 it goes to -1, and on the right side of 4 it goes to 1, one of the ways that we can find that instantaneous rate of change is we can average those two. So if we average -1 and 1, what do we get? Hopefully, you came up with 0. So now let's go ahead and apply our method of using the difference quotient to get this. So if we use the difference quotient, we're going to limit as h goes to 0. And in this case, we know what x is again. It's f of x plus h minus f of x. But I know the x is 4. So if I plug that in as 4 plus h to the original equation, so go up here to this original equation, I replace the first t with 4 plus h. I'm going to replace the second t with 4 plus h. And I have plus 18. Then I have to subtract off of that my f of 4. So if I go ahead and plug 4 into that original equation, which you've already done, hopefully you realize that that was equal to 2. That's all over h. So again, I got this 2 on here. I got this 2 right here by plugging in 4 to this original equation. All right, so looking at this, if I go ahead and I expand my numerator, I'm going to get 16 plus 8h plus h squared minus 32 minus 8h and plus 16 when I combine this 18 minus 2. And always, as I told you, that thing that you're subtracting off the end will always cancel. Well, I have a plus 16, a plus 16, and a minus 32. Everything else left has an h, so I can go ahead and reduce all of that to 8 plus h minus 8 over 1 because I've reduced. So at this point, I should have h over 1 with the limit as h goes to 0. If I go ahead and plug 0 into that, I get 0 over 1, which we know equals 0 meters per second. So doing it this way, we once again get 0 meters per second. So either way we do it, whether we use the average velocity, and in this case that worked to get the exact answer, or we use the difference quotient with the limit as h goes to 0 to find the instantaneous rate of change, we still get 0 meters per second. Both methods work to get us the exact answer. I will caution you, using the method in letter A is going to get us an approximation. We happen to get lucky that it was the exact answer in this case. All right, that's all I have for you guys for today. Hopefully everything went well. Get to work on the homework for section 2.6, both day 1 and day 2. Tomorrow we plan on doing section 2.7. We got to keep plugging along. All right, we'll see you guys tomorrow.